So in 1913, Nikola Tesla patented a new type of turbine that he called Tesla's turbine, and it was unlike any other turbine that had ever been made, or to this day. It was a bladeless turbine that could be used to generate lots of power. It was 99% efficient, couldn't produce all that much power, but it could basically last centuries and centuries and centuries without needing any maintenance whatsoever. There's actually some Tesla turbines that were made around 1913 that are still running to this day. This is a really fantastic machinist project if you're just getting into using a metal lathe and a metal mill, and you can make something really, really fantastic. Now, the engineering principles behind this turbine is really, really fun. It's something called fluid dynamics, where you're going to be using a boundary layer effect. Basically, the drag force that a fluid, like air or water or steam, basically inhibits on a surface. And if you blow really hard over a surface, it does drag, it does pull it just a little bit. So by firing air across lots and lots of discs, the drag force basically starts to spin it. It can't spin with a lot of torque, so it doesn't have a huge amount of power output, but it can spin tens of thousands of times per minute, which is incredibly impressive. Unfortunately, Tesla wasn't able to make it exactly how he wanted to, just with his time period's material sciences, but right now we can now make things as good as he ever wanted it to be. So today we're going to be working from scratch how to make a Tesla turbine, and then adding in some joints so you guys can see exactly how it would run in real life. Now, the mathematics to build these turbines are suspiciously really hard. I had to go in a deep dive for one of my theses into Tesla's original patent, and also doing a lot of research on Professor Warren Rice from the University of Arizona has done extensive research into this. So big thanks to him, but we'll be using a lot of his mathematics and a lot of his ratios to actually produce the best turbine we possibly can. So we'll be starting off by going up to our data panel, making a brand new folder for our Tesla turbine. This is where we're going to be making all of our projects. And then saving this file as an assembly. As an assembly file. And go ahead and save this, and then we can start on our first component, which is going to be called the housing. This is going to be the large ring that holds all of the pressure inside. Because all of our components are going to be symmetric about the origin, we can be making our housing from the front plane by making two concentric circles, and then we will be extruding them symmetrically on either side. We can dimension the inner circle to be 3.5 inches in diameter, and then instead of dimensioning just the outer circle, I want to say the distance between the two is 1/4 of an inch. This is a really important value because anytime you're buying large tube metal, it'll usually say what is the diameter, either the inside or the outside, whether you're talking about a pipe or a tube, and then what is the wall thickness. We're then going to finish this sketch and then extrude this profile, and because we want that origin to be right smack bang in the middle of everything, we're going to be changing our direction from one-sided to symmetric. We want to make the whole length be 2 3/16. We can just say 2 plus 3 divided by 16 in parentheses, and then hit enter. Now, this housing is also where we're going to be having our steam that will turn all of the turbine coming in from the right-hand side. So we need to be making an orifice or hole in this that is tangent to the inner edge. So let's make that by starting off a new sketch, and we're going to be clicking on the right-hand plane. And we can actually expand our sketch palette and click slice. This will give us basically a slice all the way through our geometry. And I'm going to click P for project and select this inner surface. That way we can make a circle that is totally tangent to these 2 points. So to do that, we can use our line tool and join those 2 projected points. Then make a circle, and this is going to be 0.84 inches in diameter. We want the center of the circle and our origin to be totally horizontally constrained to each other. And then we want to add a tangent relationship between the circle and that line that we just made. There we go. Now it's fully defined, and we can hit Finish Sketch. Now we can flick around our view to the side, and we want to extrude this hole all the way through. We could obviously pull this hole out all the way, or if you'd like to change your extent type to to objects and then select the outer surface, then you can see that cutting geometry maps perfectly to the curve of the outer surface that we have there. And we can click OK. We also want to add some chamfers to our piece, so go ahead and open up the chamfer tool, select the two flat faces on either side, and then you want to select the outer edge right here. If you flick around to the inside, you'll notice that as we made a tangent hole, it kind of meets up to a point. So if we add a fillet to this inside edge as well, those two fillets are going to cross over each other, and it's going to give us a big warning error. So just two faces and that one edge, and this wants to be 0.04 inches. So most of these components are going to be made out of aluminum for this project, so we can click A for appearance, and then look up our aluminum, and then click and drag this onto our project. Now that we're done with this component, we can say finish editing in place, and then we want to right click the housing and want this to be grounded. So our next component is going to be the inlet tube, which is the tube where the steam is going to be entering into our housing. So we're going to be making a new component called inlet tube, and we want to make sure that the location isn't just set to our joint, but it's actually set to our Tesla turbine folder. And then we can click OK. Now this isn't a component that we want to be making in the edit in place window, so we can just open up our data panel and work on it as its own separate tab. So for this component, we are going to be making a sketch on the front plane, and it's going to be consisted of a rectangle, a very long skinny rectangle, and then a couple lines to make a triangle. Now for all of our constraints, we want this bottom point of the triangle and our origin to be totally horizontally constrained to each other. And then we also want this left vertical line to be coincident with our origin. Now for all of our dimensions, this outer radius is going to be 0.42 to be mating with that 0.84 inch hole that we made in the housing. The inner radius is going to be 0.31 inches. The entire length of this tube wants to be 3 inches long. And the distance from the most right-hand point of the triangle to the end of our housing is going to be 0.4 inches. And then the angle of this triangle is going to be 30 degrees. So when we revolve this sketch about the red x-axis, you need to select both of the profiles and then the red x-axis, and this will give us a totally sealed off tube. But what it's going to do is add a pretty perfect funnel for all the steam to be compressed into it. And our next step is going to be making a series of holes that we can direct the steam in as efficiently as possible. So to do that, we want to make a brand new sketch on the end face of our tube. And with our circle tool, we're going to be making 5 circles, all exactly the same size. We can click and highlight all of them and apply an equal constraint to them. And these want to be a 1/16 of an inch. That is a perfectly normal sized drill bit that you'd find to do this operation. And then each of them want to be 0.1 inches apart from each other. What this operation is going to be doing is basically making the inlet totally planar. So we don't have a big hole that's going into just a couple blades. We're actually going to be distributing it along an entire face. The last thing that we need to do for all these is make sure that they can't move up or down. So I'm going to be holding down Control and then selecting all of the origins of all these holes, and then adding a horizontal constraint to these. And as soon as we finish this sketch, we can extrude all of these 5 holes. And we don't really need to have any dimension specific, just as long as we can click and drag and have it cut all the way through, that's fine. And then as you can see after hitting OK, that we do in fact have those holes cutting all the way through our piece. Now very often steam is being run through high pressure, high temperature resistant pipes. And anytime you're in America and you're talking about pipes, there is in fact a pipe threading standard called an NPT. Unfortunately, we don't have this capability for external threads within Fusion360, but we can get pretty close by adding an ISO pipe thread. The only difference is that the TPI is slightly different, and in US NPT pipe threads actually have a taper to them because they're really so heavy, making it easier to basically screw in is everything. So we can go to our threading tool and click on this outer face. We don't need it to be the entire length, so we can uncheck that full length and say we only want it to be 0.75 inches long. We do want this to be a modeled thread, but for the thread type, we're going to be changing this down to an ISO pipe thread. Again, slightly different, but pretty close. Then we can finish off by hitting OK. Just like we always do, anytime we have a manufactured thread, we want to cut off the little edge on there. So we can make a sketch on the front plane. Using our line tool, make our little triangle, give these two edges equal lengths, and these are going to be kind of a chunky chamfer on there. Again, pipe threads are really, really tricky to get in place, so having a large chamfer on there is just going to make life so much easier. So that's why we're going to make these 0.08 inches. And then we'll just click and drag this where it's supposed to be. We can click P for project and then select the outer edge, where we can make this totally collinear to. And because we know the outer diameter of this piece is 0.42 inches in radius, we can just type that in based on the distance to the origin. Then we can have a revolved cut thread for all of this about our red x-axis. And as you can see, this gives us a very nice large chamfer. Now this part is also going to be made out of aluminum, so we can click A for appearance and type in ALUM, and you can see it's popped in right there. And if you find that you use this appearance all the time, you can always right click and add it to your favorites. I already have it in my favorites just because I use it all the time, but instead of having to type it through every single project, please just add it into your favorites. It saves a ton of time. But we can close this out and then save this file, and then head back to our main assembly and then update this file. So now that we have our two components, our main housing and our inlet tube, we can click and drag around this in a way that's not ideal. So let's add a joint between these two. So we want to make sure that we have a joint between the outer edge of our circle, and then even though this is not a perfect circle, we can actually click on it. And as you can see, as I move my cursor around that curved hole, there are these two endpoints where I can snap to, and that's where I want to click. Then it moves it over. But this is still set to a revolute joint from the pizza cutting class, but we'll just make this into a rigid grounded joint. But we also want to click on one of these arrows and pull it out a little bit, because we want to get access to all those threads. So we'll be pulling it out 1.25 inches and then clicking OK. So as we can see with our two components right here, our inlet tube is actually crashing into the inside of our housing, which we really don't want. So we can actually use the edit in place window to help us cut out this section, because it's going to be based on the geometry of the outer housing. So we can go over to our browser, put our cursor over to our inlet tube, and then click the little pencil icon. And then we can make a new sketch on that front plane, which, as you remember, cuts right through the very middle of the housing. Then we can click P for project, and then select the inner surface, or the inner ring. There we go. And then click OK. And now we have a profile that we can now extrude cut symmetrically. If you change your direction to symmetric and then pull it either side, you can see that we completely cut away the unnecessary material for our inlet tube. And then by hitting Finish Edit in Place, it is now perfectly cut. Now our next components are going to be two gaskets that you can be finding on either side of the wall. These are basically two rubber discs that we can apply pressure to, and it will hold the steam in really, really well. They are two very, very simple components, but they need to be in the right location or else they won't work. So it'll be making a new component, and this one can just be called gasket. And after we click OK, we can just be making a new sketch, not on the front plane, but actually on the outer face of our housing. Then we can use our project tool and select the very outer and the very inner edge and click OK. Now this gasket does not need to be very thick, so we can just finish the sketch and then extrude out these profiles. And we just want to pull them out 0.03 inches. Again, gaskets do not have to be very, very complicated, but they are very, very important. If we didn't have gaskets, then we wouldn't be able to hold in any pressure or any fluids, inside any of our mechanical systems. We can also add in an appearance. Gaskets are usually made out of either cork or rubber. So I'm just going to be adding in a soft rubber appearance to this. And very often, gaskets come in all different colors. One of them that's really common is a bright red. So we can double click on the rubber and then change around the color to the top left corner. And this will give it a really nice, lovely red. Now this component is all done, we can say finish editing in place, but we do want a gasket on the other side. So instead of having to make another one, we can actually just click M for move and select the component of our gasket, and then move it over with our create copy already checked. And we can move it over until it's about in the right location and then click OK. Now our right gasket is in the correct location, so we can make it fully solidified by using the as built joint by selecting the housing and then the component itself and then clicking OK. But our other gasket is kind of free floating, and this is where we can put in our joint. We want this face to be fully secured with our housing, and we want our joint origin to be right at the very middle. So we can select either this outer edge or this inner edge, but it's really important we select on that wall. Then we can flick around the other side of our housing and select either face or either edge. And then those are fully mated, and we can finish off by clicking OK. Now in an industrial setting, gaskets are usually made just by punching them out with really big steel knives. But another way to cut gaskets is just to laser cut them. If you go down to your local library, it is a good chance that they actually have a laser printer and a set of 3D printers that you guys can use. So in the gasket, in the browser, we can actually expand the sketches area. So it says sketch 1, we only had one sketch, and then right click it and you'll be able to see we can save those two circles that are the right dimension as a DXF. This is kind of like a 2D PDF vector that laser cutters can use really efficiently. So you can save that if you'd like to make this in real life and if you have access to a laser printer. Now our next component is going to be our central axis. This is what all of our discs are going to be held to, and it's what's going to be revolving around all of our housing. So we can make a new component. Like I said, this one is going to be called the central axle. And we want to be making this as its own separate file. So we don't even need to finish it in place. We can just save this file and then open it up as its own standalone file. To make this project, we can just go into Create, Cylinder, and then select on the front plane. Remember, this is going to be extending away from us. So we can click on the origin and pull outwards. This is going to be a 0.25 inch diameter rod. Hitting enter, and then we want to be extruding it 3.5 inches. Now we're going to be having some cutouts on the top and on the underside of this central axis, and that's how we're going to be joining all of the discs to some of the mounting hardware to the central axis. These flat sections are going to be a really good area for some set screws or grub screws to tighten down really well. So to make these, we're going to be opening up a new sketch on the right-hand plane this time. I'll be making two rectangles. And these are going to be having the exact same width and the exact same height. We can also add in a collinear relationship to the underside of both of them. So as soon as we move one of them down, it moves the other one down as well. So to dimension these, we want to say that the underside of these rectangles to the origin is 0.1 inches away. We can say the distance from the left-hand side of the left rectangle is 0.45 inches away. The distance from the outer edges between the two rectangles is 1.94 inches, and the width of both the rectangles are 0.2 inches. Very, very small. We don't really care about the height of this rectangle. As long as it's above our central axis, that's fine, because we're just going to be cutting them through. We can finish this sketch and then extrude out those two profiles, and we want to be making these symmetrically extruded out either way. We can click OK for this, and then we want to mirror that feature, that extrusion, about the very top plane. So we have two of the flat sections on top and two of the flat sections on the bottom as well. And because this central axis needs to be really incredibly strong and it needs to withstand a lot of rotation and a lot of torque, instead of aluminum, we are going to be adding a stainless steel appearance to this. Now we're going to be adding some chamfers to the ends of our edges, so they're not super duper sharp. These can be 0.02 inches, nothing too major, and this component is all done. So we can save this and then go back to our assembly file and update it. But because this is a part of a sub-assembly, I don't actually need it to be right in the middle of all the other components. This is actually going to get in the way really quickly, so you can just click and drag this away from it. So we'll be having basically two different sub-assemblies. That will be the housing, or the stator, and then all of our discs, which will be the rotor. So the stator is stationary, the rotor is rotating. Now our next component are going to be things called brass shoulders. These are basically going to be two large chunks of metal that we can pass a thread through, and so when we put in all of our discs, these will be able to compress and add a good sense of stability to these. Brass is a really easy material to machine in metalworking, but it also has a pretty substantial density. So when we have all this high RPM, because we have such a high weight associated with it as well, we can produce much more torque. But all of the weight is going to be closer to the central axis, so we have a higher sense of stability with it as well. So we can click OK, and just like before, we are going to be making this not in the Edit in Place window, but as its own standalone file. Now to make this revolved part, we're going to be making a new sketch, and we're going to be working on the right hand plane, so all of our components are about in the right location. And using our line tool, we are going to be making kind of a letter L on the left hand side of the origin. As far as constraints go, we're going to be adding an equal constraint to these two top horizontal lines, and we're also going to be adding a coincident relationship between this vertical line and the origin. Now, as far as dimension goes, we want this to be riding over the central axis. So we're going to be making this radius 1/8 of an inch. We also want to make this top flat section 0.2 inches. We want to make the outer radius of this little shoulder right here 0.225. And the entire radius of this back section is going to be 0.45 inches. So we're going to finish this sketch and then revolve this profile around the green y-axis. And then we need to have two holes, one on the top and one on the bottom, to allow for two really long bolts to pass through. So we're going to make a new sketch on that on the shouldered plane, and our two circles are going to be equal diameter. So you can just add a little equal constraint to both of those. And then we also want them to have a vertical connection to the origin as well. Now the diameter of this circle is going to be 0.112. This is a funky number because it's going to be the drilled diameter of what is going to be tapped, which is always kind of a strange one. But the distance between the center of the circle and the origin is going to be 0.338. And that's going to put it smack bang in the middle from this top point to the top of this outer circle. And we're going to do the same thing for the underside. We can now extrude these two profiles all the way through our parts. Again, doesn't really need to be anything too crazy. As long as they cut all the way through, we'll be okay. We also need to add two drilled holes that go perpendicular to our axis. So we're going to make a new sketch, this time on the right plane, and we can also cut it in half if we'd like. So we can always click slice in our sketch palette. And we're going to be making a circle that is horizontally constrained to the origin. And this is going to be 0.112, the same diameter as our upper pieces. We can project this entire internal bore. And then we know that the center of the circle wants to be 0.1 inches from that outer face. Now this circle that we've made wants to be symmetrically extruded either side. So go ahead and change your direction to symmetric and pull it out so it cuts all the way through either side. And then we want to add a nice little chamfer over the entire thing. So go to your chamfer tool, highlight your entire piece and make it 0.01 inches. There we go. Now we're going to be adding a threaded feature to all of these holes that we just made. So we can select all of these inner faces while holding down Control, and it should automatically go to a 440 unified thread. We want this to be a threaded feature, and then we can just click OK. And because this is a brass shoulder, we want to go ahead and add a polished brass appearance to this as well. And this component is all done. So let's go ahead and save it, and then go back to our assembly file and update it. So we can click and drag this brass shoulder over to our central axis, and this is where we can add a rigid joint to it. So add your joint, and we want to click the outer edge of our brass shoulder, and we also want to do the same thing to our central axis where the notch is closer to the edge. And as soon as we do this, we also want to rotate our piece 90 degrees so that the threaded hole lines up with the flat section on our central axis, and we want to pull this in 0.45 inches. This is really nice because it means the very center of our bore will go right into the dead center of the flat section that we made in our central axis. And then click OK. Now the next component that we make, this will be the really important one. We are actually going to be making the discs which will actually be able to spin our rotor. So let's make a new component. This one will be called a rotor blade. And by clicking OK, and we want to make this in its own separate tab as well. For this sketch, we want to make it on the front plane. And because this is a rotor blade, we're going to be using the circular tool to make a really large outer circle, another smaller concentric circle that will fit over our central axis. We want to make two small circles on either end that will be passing through our brass shoulder, and then one larger circle just above. We can add all of our constraints to these, so we can click the center of all of these three horizontal circles and add a vertical constraint to that, and then one vertical constraint between these two circles as well. So we'll start off our dimensions by setting this inner circle to be 0.25 inches. That will go over our 1/4 inch axle. These two circles will end up being 0.125 or 1/8 of an inch, and we can also add an equal to both of these circles so they become the same diameter. We also want to set the distance between the origin and that circle to be 0.338 so that it lines up with the holes that we drilled out on the brass shoulder. And we'll do the same thing for the other side. Now this outer circle here, this is actually fairly interesting. So this has to fit inside the internal diameter of our housing, so 3.5. But because of all of the fluid dynamics, we want it to be just barely smaller. In fact, we want it to be about 2% smaller, so that we still have some wiggle room so the blades don't accidentally rub up against the inside of the rotor, but we don't want to have any fluids, or minimal fluids, actually just spinning around and not exiting through our system. So we can type in 3.5 multiplied by 0.98. That'll give us the 2% smaller that we're looking for. Now this top hole right here, which we will dimension to be 0.188 in diameter and 0.55 inches up from the origin, this is going to be our exit hole. This is where our steam is going to be passing through our discs and then out of the housing essentially. But just one hole isn't going to work for us. We need to add a fair few more. So let's go to our circular pattern, select our circle, our center point is going to be our origin, and then we're going to be making 6 of these holes. So with the sketch all done, we can finish it and then extrude this surface 0.015 or 28 gauge aluminum. We also want to be adding on one of our polished aluminum finishes to this, as these are made out of really thin aluminum. And then we can save this part and then go back into our assembly, and this is where we can fit it over our brass shoulder down there. So we can bring that over, and we want to make sure that in our joint that this face and this edge lines up with the other side or the underside of this bolt of our brass shoulder right there. So this will mean that both the rotor and the brass shoulder are absolutely perfectly fit together, and they both line up on the same axle. We also want to verify, if we go around to the back view, that yes, the holes that we have going through our brass shoulders and the holes that we have going through our rotor blades are totally aligned. If for some reason when you were making this, it brought it in sideways, then you wouldn't be able to see the through holes, which we don't want. So we can just click OK for that. Now our next components are going to be the spacers that fit in between one of the discs and then the next discs. And these can be made out of the exact same material. And the reason that we chose such a thin bit of aluminum is because, funnily enough, the ideal width between two discs, or that gap, which is the most important part of this entire turbine, is 2 times the thickness of this blade. So for every gap in between them, we'll just insert 2 of these spacers. So let's make a new component. We're going to be titling this the Rotor Spacers. And again, we're going to be making this as its own separate individual file. For this component, we are going to be making a new sketch on the front plane. This will be a large 0.9-inch circle. This is basically just going to crest just below those 6 holes for the outlets. So these spacers don't block the steam from exiting. We're also going to be having a central 0.25-inch hole going through the middle that will slide over our central axis. And then we also want to have 2 circles on either side. These can be totally equal in diameter, and we can make the very centers of these 3 circles totally flat. Oh, there we go as well. The distance from the center to these circles, again, is going to be 0.338 on either side. And then the diameter of these holes is going to be 1/8 of an inch. And then when we exit the sketch and then extrude it, it's going to be to the exact same thickness, so 0.015 inches. Again, this is always going to be the same material, that polished aluminum that we have. And this component is all done. It's a nice and fast one, which we like. Going back to the assembly, we can update this. Our component is going to be, there we go, it's a little hiding. And then we can add our joint. So again, we can add it to the inside face. There we go. And then we'll flick around to the other side of this joint and select it there. And then when we click OK, you can see that we have got, if we pull it out, we can see that we've got our rotor disc right here, and then our spacer just in front of it. Now, like I said, we do want to have 2 of these. So I'm going to click M for move, and I'm going to select the spacer as the component that I want to move, but I also want to duplicate it. So let's check create copy, and then let's move this out the thickness of our material. That would be 0.015, and then click OK. And as you can imagine, because it's already in the right location, we can just use an as-built joint to connect these 2 components, and then click OK. Now, just one disc is not going to be tremendously useful. We're not going to get a ton of power output out of this, so let's add a bunch of them. In fact, we need to add 25 more of these. So we're going to go into our Create menu, Pattern, and then Rectangular Pattern. For our type, we want to change this over to Components, and the object that we would like to multiply are going to be this large rotor disc, and then our 2 smaller spacers. You could also go to your browser and select these 3 as well. The direction that we would want to pull it is going to be in the green y-axis, because we haven't rotated this subassembly at all. We've just translated it within the workspace. We can pull them away. Like I said, we want to make 25 of them total. And then instead of the extent, we're more worried about the spacing. We want them to line up and nest really neatly. So the spacing between all of them is going to be that 0.015 multiplied by 3. We don't need any in the other dimension, so we'll just leave that as 1. And then click OK, and you can see we have all of our discs in place. Great. And then to finish off this stack of discs, I'm going to click M for move, select the most recent disc. I'm going to say create copy, and then pull this out the distance of 3 times 0.015, which will line up perfectly with the rest of all of our discs. There we go. Now currently, if you take a look at the browser, you'll see now every single spacer and disk that we have is now on one gigantic list. And instead of the browser being a really organized place to see all of your components and sketches and everything associated with it, it is now just a jumbled mess. It's a minefield of really, really difficult things to see. And to be honest, I don't care about most of these components. Rotor spacer v2.6, I don't really care about it. So you may as well compress all these into a single sub-assembly. And that's exactly what we're going to do. We are going to be making a new component. This time it's going to be an internal component. And we can basically group them all together to say all of the disks and all the spacers are in this internal sub-assembly. It is internal because it is inside the main top file. So by clicking OK, you'll see it pops up right at the very bottom. So we want to highlight all of these inside our browser. So we can select the very top rotor blade that we have, scroll down to the bottom, hold down Shift and click the bottom rotor blade. This will highlight all of the disks and spaces in between. And then we can just click and drag this into the sub-assembly essentially. And now you can see it is all compressed in there. We've got our main assembly, and then we've got our sub-assembly over here as well, which is really nice. We can also do a similar operation to our timeline as well. We can select the very first feature that we have right here, which is basically just saying move this component to a sub-assembly file. Then we can zoot over to the other side of our timeline, hold down Shift again, click that last feature, and then this will highlight every single one of these features that we can then right-click and create a group, which will push them all together. So now we've got all the features nice and organized, and all of our components nice and organized. But currently they are all still free floating. And so because we have way too many components to individually go and as built joint for all of them, we can just add in a rigid group. So we can just select this internal component which houses all of our components, hit yes, hit OK, and now it has fully rigidly locked all of these. So like I said, we do only have one brass shoulder. We also want another one on this backside. So again, we're going to be using M for move. I'm going to be selecting this component, hitting create copy, and then moving it over to the other side. And we do want to rotate this 180 degrees, so it's in the right orientation, and then click OK. And then just by typing J and adding in a perfectly normal joint, we are going to be selecting the inside ring of this brass shoulder, flipping our view around and clicking the outside edge of this rotor blade. That'll push it into place, and then we can always get a head-on view, there we go, to make sure that we do have a hole running all the way through both of our brass shoulders, and then clicking OK. Now to join all of these components together, we can insert two really long skinny bolts through the threaded section of the brass shoulders, and we can do this by adding in a McMaster-Carr component. So you can just type in your code that you can grab from your packet, and this will add in a very long 1.5 inch 440 thread. Again, we don't want to add in a SolidWorks file, we want to put in a step file, which is very similar to an STL that we use in 3D printing, and then we can download this. So we'll click and drag this component a little closer to where it needs to be, and we can also rotate it so it's in the right orientation. This isn't absolutely necessary, but getting it about close does help. Then we can add in a joint to the underside of our bolt, flick our view around, and then do the same thing to the outside of the brass shoulder. This will now insert this, this bolt all the way through one brass shoulder and then screw into the backside. To make the other bolt, again, we're going to be typing M for move, selecting our bolt component. I would like to make a copy, and then I'm going to be moving it over to the other side. And because we know the distance between these two, we can just type in negative 0.338 times 2. So it puts it perfectly on the other side, and then clicking OK. Now this bolt is already in the right direction, or in the right location as well, so we can just have an as-built joint between two of these components. Any two components work, to be honest, and then everything is rigidly locked together. To join the brass shoulders to the central axis, we're going to be putting in some more hardware. We're going to be putting in some things called grub screws or set screws. We need 4 of them, and they're going to be going through this perpendicular hole and then setting onto the flat section that we cut on that central axis. So we can open up another McMaster-Carr component and looking up this file. It's already set to 3D step file, so we'll just download that and then bring it roughly into place. Then we can click J for joint, and we want to add it to the underside of our step file. And here's kind of a funky thing. If we have almost a square or a rectangular shape on anything, you can snap to all corners of it and the very center, which is really handy. So if we get a top-down view, you can see that we can snap to that middle, and there we go, it's already put in place. We don't need to take away the brass shoulder or hide or do a cut or anything like that, already built in place. So now I want you guys to create 3 more of these bolts and put them in the right locations. Our next components will be the 2 walls that will cap off either side of the housing. So these again are going to be going back to the external components, and we're going to be making the first one called the power side wall. This is going to be located on the left-hand side where all of our power transfer can actually go towards a generator. So we don't need to edit this in place, we can make this as its own separate file. So to make this, we'll be making a new sketch on the front plane, and we'll want to make a center rectangle at the very, very center first, and then we'll be adding on some 1/4 inch radii to each corner. The radii we can put in a dimension right now. It doesn't really make too much of a difference, but we also want to add in some equals to the 2 walls. This will make it a square with rounded edges essentially, and we can dimension the entire width to be 5.25 inches. We also want to be adding in a center circle that is 0.55 inches in diameter. This will then house a bearing that we're going to be putting in a little bit. We can also put in another circle in a top corner that is coincident to these construction lines, and these circles want to have a diameter of 13/64. This will give us just enough clearance for our bolts to pass through these holes, and these want to be 1/2 inch from the edge. Now we do need 4 on all corners, so we may as well add in a circular pattern. So we can say that's the circle that I would want to pattern about the very center. I would like 4 of them, and that pops them right in the same location. Then we can extrude this part out to 0.25 inches. And we also want to make a new sketch on the front plane of our piece. And we're going to be making 3 concentric circles. We're going to be making the internal circle 3.5, and then the distance between these 2 circles as 0.25. This is what is going to be mating with the housing that we have. And then this inner circle is going to be just slightly larger. It's going to be a 5/8 of an inch, or 0.625. We are basically going to be having a recess on this face where the housing can slot into, and we're also going to be having a second recess where a bearing can be pushed into the middle here. Now the extruded ring can be cut in -0.125 or 1/8 of an inch. So go back into your browser and expand your sketches and turn on a second sketch. And then we want to extrude this ring right here, but we don't want to extrude it in just normally. We want to actually have a certain offset because we know the thickness of our bearing and we want our bearing to live on the outside. So we can set our profile plane to actually be an offset. And this offset is going to be -0.054 inches, and it's going to be cut all the way through. So what that'll do for us, it'll leave just a little bit of material so that our bearing is totally flush with this back wall, which is really nice. And then we can turn off that other sketch. Again, we want to make this a polished aluminum part, and then this component is all done. We can save this and then go back to our assembly file, and then this is going to be living on the back side of our component. So we can add in a joint to the inside edge of our power side wall, and then the outside edge of our gaskets. Perfect. And this can be revolved 90 degrees, 180, 270, doesn't really matter. As long as it's kind of head on nice and square and flat, that'll work just perfectly for us. Now we also want to make another component that is basically identical to our power side wall, but on the other side. It's basically just going to be a mirror image. Mirror image, mirror tool. So we'll go up to our create menu, select mirror, make sure your type is set to components. We can then select our power side wall, and then our mirror plane is just going to be our front plane essentially. And then as soon as we click OK, not only is it already in the right location to add a joint, but it's all of the geometry is exactly the same as well. You'll notice if you go down to your browser that it now says power side wall mirror. So you can always just select this and then double click it to rename it steam side wall, because we're going to be doing some degree of changing on this as well. Now we can go and work on this piece individually. So you can always select that component, make a new sketch, and then we want to make two sets of circles that are right on top of each other. We're going to be adding a vertical constraint to the origin and the centers of these two circles, and we can set the distance between the origin and the center of the top circle to be 1.25, and that is going to be having a diameter of 0.19. For the bottom one, the distance between the origin and the center of it is going to be 0.55 inches, and this is going to be having a diameter of 3/16 of an inch. So now we can finish this sketch, and we want to make an extrusion cut, not through all, but actually just to the other side of this object. And then click OK, and this is where we can start to put in some of our patterns. So we want to be making a circular pattern of this bottom circle here about our green y-axis, and we would like 12 of these. And what these holes are the outlet ports of all the steam coming out. We're going to be making a little funnel nozzle in a little bit, but we want to make sure that the total total cross-sectional area of all of these holes added up is equal or greater to the orifice of the steam coming out. If these holes are slightly smaller than the combined surface area of the hole going out, then this is now a throttling point, and you're basically losing a ton of efficiency with your process. So we don't want to do that. What we do want to do is add a threaded hole to this top section. This was going to be a 1024 threaded hole. We also want to pattern the top hole and the thread it has as well. So we're going to go into circular pattern, change our type to features, and this will include both the thread and the extrusion. Now technically we are patterning this hole below it as well, but because we want to have only 6 holes of this, and 6 is divisible by 12, we won't cause any issues whatsoever, because we're basically cutting out the same hole where there is also a hole anyway, so no problems whatsoever there. So with this component totally done, we can actually go back and activate this top component and then add an as-built joint between it and really anything else that touches it. And this will be a rigid joint. And what you may not have noticed that the entire time through working that is because we copy and pasted this, there is now a link between these, which makes this technically an internal component. So we could have made this as an external component or as an internal component. Both of them would do the exact same process. Now the bearings that we have for these are also going to be from McMaster-Carr, so go ahead and type in your components and we can be downloading our step files. These are kind of already in the wrong location and orientation, so let's flip them around so they're looking a little closer to what we need, and then we can just add in a perfectly normal joint between our component, or our bearing in this case, and then the inside of that edge right there. That'll put it into place. Perfect. We can also do a similar thing that we did to the steam side wall, where we have a mirrored component, which would be our bearing, about our front plane. Click OK, and then this is already in the right location, but it's not locked in place, so let's add an as-built joint. Now to apply pressure between the two walls to actually make a really good seal, we need to pass some bolts that go right the way through it. But what can really easily happen is as you tighten, you actually bend these metal plates inwards. That may cause a gap, and then steam can just rush out really easily, and then your two plates that you spent a long time manufacturing are trashed. So what we need to do is put in some compression stems. These go by lots of different names, spacers if you'd like, but basically just a little cylinder that extends from this wall all the way around to the other wall that are also threaded. So when we pass some bolts through on either end and we know the exact distance that they're supposed to be, as soon as we bottom out on everything, it's already nice and good. So to make these new components, these are going to be external and they're going to be named connection posts. And we can actually make it in the edit in place window. We can make a new sketch on the inside face of one of these walls. That can be a little hard to see, but we're just going to be making a little circle that is 0.375 inches in diameter. And then click Finish Sketch. We can now extrude both of these profiles and make them go all the way to the other surface. So we basically have a little cylinder that is the perfect distance in between both of these walls. And we can add on a little polished aluminum finish to that as well. And then we also want to add on some threaded holes on either end as well. So let's click H for hole. And by clicking through this hole there, we want to select the top face of one of these cylinders, and we can click and move this to the origin. This wants to be a number 10 thread, or 1024 to be precise. We do want this to be a modeled thread, and we really don't care if it has a little chamfer to it, but it would be nice. So let's make that 0.25 inches and the exact same 0.625 inches of depth. We can also mirror this feature about the front plane, so add the mirroring tool. The features that we'd like to mirror is going to be that hole that we just made, and it's going to be about the front plane. There we go. Now we can finish this component, and then we can pop in the two bolts that are going on either side. Again, this is going to be a McMaster car component, so we can go ahead and pop these in. We will be needing two of them. So as soon as we pop them in, we can make one of them into the right location and then make the other one on the opposite side in the same way. So you'll notice that we actually only made one of these posts and then two bolts on either side. And that's because we have made everything about the origin. So instead of making three more posts, joining them up and doing all that process over again, we can just go into our create menu and add a circular pattern between all of these components. So much easier. Saying exactly where the origin is, it dictates how I model things. If you can be kind of clever and have a bit of forethought about how your model is going to be manufactured, how it's going to be made, how the best way to design it is possible, and then kind of put it in relation to the origin, it makes life so much easier. So we can set this to 4 times the quantity and then click OK. And then down in our browser, you can see we've got 8 bolts and 4 connection posts. So these are all of them that we can actually pop in some rigid joints to. So we can click the top one, hold down Shift, click the bottom one, and then add in a rigid joint to lock all of them together. So now that we have our 2 sub-assemblies totally done, we can now put them in the right location. Now, obviously, we want to have our central axis be, or have a revolution joint to our bearing. That's obvious. But exactly where does it need to be? We want to centralize it as much as possible, but how much on either side do we need to give a gap? And that's where we can actually do a little bit of an inspection using our measure tool up here. So I'm just going to go ahead and add a section analysis to the top plane, so we can kind of peer inside, and it'll be a lot easier to see what's going on. And the important thing to notice is that if I measure the distance between either wall of my bearing, and then measure the distance between my brass shoulders, and I subtract those two values together, and then divide it by 2, that will give me the perfect distance that I need to move my brass shoulder, so it's exactly in the middle, which is exactly what I'll do. So if I go to my measure tool, I can select my bearing wall, flick around to my other side, select that, and it looks like it's saying 2.106 inches. Great. So I can write that down, and then we can go back to our measure tool, go over to our brass shoulder, say, all right, then what is the distance from that wall, flicked over to that wall. And it's saying this is 1.94 inches. Great. So if I take those two values and divide it by 2, that will give me a gap of 0.083 inches. So now if I go to my joint tool, I can then select that ring for the outer face of the brass shoulder, go around, do the similar thing to the little bearing right there, but this will give me a rigid joint, which we don't want. We want this to be a revolute joint. There we go. That'll give us a little animation of it spinning around. Perfect. So then as we click, or before we click OK, excuse me, we need to move this over. We need to pull it over 0.083 inches, and that'll give us the perfect gap on either side that we're looking for. And then by clicking OK, there we are. Our two sub-assemblies are now one. Perfect. And we've got a nice and even gap on either side. And because we added a revolute joint, you can actually grab this and spin it around. It's got the top chopped off, but you can kind of see exactly what's going on. So by turning off the section analysis, we've basically got our axle that is totally secured in CAD, but not in real life. We need to add two more components, something called a retaining ring, which basically is a little C-shaped bit of metal that can go around our retaining ring, and it prevents it from moving side to side. This is where we can put in a little bit of an edit in place magic, where we can cut out a groove based on the components that already have in place, and then pop in the correct components. So we're going to go over to the central axis on the browser, and we're going to be clicking the edit in place window. That's fine. Then we can make a brand new sketch that is on the top plane, right there. And we are going to be projecting either wall of the power side wall and the steam side wall. This will allow us to basically make sure that our grooves are exactly snug to either side of the wall. And we're just going to be making two small rectangles on either side. And these are going to be having equal widths, equal heights, the whole deal. And then we also want to add a collinear relationship between the bottoms of both of them. We also want to be adding a collinear relationship between the left-hand side and the right-hand side of both of the walls. Now the width of this cut is going to be 0.029. That's the same thickness as our retaining rings that we're going to be putting in there. And we also want to say the distance from the very bottom of this groove to the origin, this wants to be 0.115 inches. So it cuts in just a little bit. And then we really don't care, again, how tall this rectangle is, as long as it's above the top of our central axis. It doesn't really matter too much, but we can click Finish Sketch now, and then make a revolution cut of both of these profiles about our green y-axis. And then click OK, and now we've got nice square grooves in all of this. Now we can bring in that retaining clip, or actually both of them, by inserting the component from the McMaster-Carr plugin. Go ahead and download it and bring it over to one side. And then you can rotate it to make sure it's in the correct orientation. And then we can go ahead and add a joint between one of the rings of our retaining ring and then the outside of the groove as well. And we don't need this to be a revolute joint. In real life it is, it can free spin, but it isn't super necessary. So if you want to, you can just make this a rigid joint as well. And then we can click M for move, select our component, which is going to be our retention ring. I would like to create a copy, and then we can just bring this part out to the other side and then make a similar joint to lock that in place. Now our last two components that we're going to be making will be a gasket that goes around the outlet and then an outlet nozzle. So we'll start off with the gasket by making a new component. This one is creatively called outlet gasket. And this is going to be made in the edit in place window, but by creating a sketch on the steam side wall on the outside face. And we are going to be using a set of circles starting from the origin to define the outside of the gasket, the inside of the gasket, and then we're just going to be making a very simple 1/4 inch hole that passes around one of the threaded 6 holes that we have. We can dimension this inner circle to be 1.55 inches. 1.55, there we go. And then the outer one to just be 3 inches normally. And then we are going to be extruding this, just this profile, at 0.03 inches, just like we did for the other gaskets. And then that can receive the exact same soft rubber appearance that we had for the other ones. Again, we can make this a lovely little red, add some color to the design, which we always like. Now with this component done, we can just put in an as-built joint to lock it in place. Now for our last component, this is going to be our outlet nozzle. And we are actually going to be making this as its own separate file. So let's go ahead and say finish edit in place, save this whole assembly, and then go off to our file out here. And we're going to be clicking on the outlet nozzle right there. Now for this object, we are going to be making a sketch on the right-hand plane, and using our line tool, we're going to be starting by making a vertical line just above the origin, going down at an angle, horizontal again, and then just following that profile up and around. This line wants to be horizontal, and oh, it's already done it, but these 2 angled lines, these are going to be parallel, and we can just put in all of our dimensions. So let's go ahead and finish this sketch and then revolve that profile about the green y-axis. That'll give us this kind of funky funnel shape. And then we'll want to make a new sketch on the backhand side. And this will be a very simple circle that is 0.25 inches in diameter, is vertically constrained to the origin, and can be found 1.25 inches from the origin. There we go. Now we can go ahead and extrude this profile all the way through our piece. And then just like the gasket and the other threaded holes in our steam side wall, we would like to add a circular pattern. Our features that we would want to pattern would be that extruded hole all the way about that green axis. We want 6 of those babies. There we go. We can add a very light chamfer by highlighting the entire piece and setting it to 0.02 inches. And then we can add on our polished aluminum finish to it. That's great. And then because this is an outlet, we want to be able to put on another pipe thread onto there. So that's why we can add on a little thread onto that section right there. We can change this to an ISO pipe thread, model it, and then click OK. And this component is all done, so we can just save this part, go back to our assembly, and update it. So we can grab our component and then add a pretty normal joint to this, where we can say, yeah, it should line up with the gasket, or the holes should line up nice and neatly. And because we already made it in the correct orientation, there won't be any twisting artifacts to worry about. Now the last thing to do is add on 6 bolts that go through the gasket into the steam side wall. Conveniently, we can actually just use the bolts that we used previously for our connection posts. So let's click M for move, select any of the bolts you'd like. I would like to create a copy, and then move it out of the way. Then we can add in perfectly normal joint to just one of the holes on the outlet nozzle. And with the power of circular pattern, we are going to be adding a circular pattern from this component and rotate it 6 times about the green y-axis. And that will evenly space all of them perfectly. And then we can just add on a rigid group between not only our outlet nozzle, but then also these extra 5 bolts that we passed on, and then clicking OK. And this part is all done, so we'll give this another section analysis so we can take a look at the inside of this, and we have a fully functioning Tesla turbine, and I will see you guys next week.